Okay, so part 2, after all that stuff, so on example 6. We did that stuff in the calculator before, or you kind of watched me or talk about putting it in the calculator. We'll do more of that. The idea is you can do it with the calculator. Ultimately, we get away from doing that. We're just justifying things as we go with the tools that we have. But this series now, this 3 over 2 to the n, now think about what we've done in the past with limits. That's definitely growing faster in the denominator, so it'd go to 0. That means these terms, as they go out, you see them all those terms, 3 over 1,024, even that's getting close to 0. So we start with adding, you have 1.5 in the beginning, then we add 3/4, and then we keep adding smaller and smaller amounts. It kind of makes sense that maybe it might converge to a number, but it doesn't always have to. So you guys remember we did that penny test, we did half a penny, and we kept adding half and half and half, and in one case it converged to an amount, a certain number of pennies to 2 pennies, and then one case it did not, and there is a subtle difference between it. So it doesn't always, by adding a smaller and smaller amount, doesn't always converge to something, but we do recognize that we're adding smaller and smaller pieces. That makes a good case that it might converge. So we need something more sophisticated. We're going to play it out with some numbers. Let's do some partial sums. Like s of 1 would just be the first term added. S of 2 would be the first and second terms added. That kind of thing, and so on. We could add this up. Calculator does great things. Sum of the sequence. Here again in the button sequence. Second stat gives you the list. Go to math and you find sum. And then if you do the second stat and go to ops, you'll find sequence. And you can you can put in the rule, 3 over 2 to the n, and then do a certain number of steps by, it's always steps by 1, but I'm going to go, let's say, to 10 on my calculator, and I got 2.997. If you compare it with the prior sums, we're trying to decide, is that growing or is it kind of staying the same? And S of 10 is probably not big enough to find that out. So if we go to 999 on the calculator, it'll give you this message called overflow. So let's take a peek at all this so far. We're just looking at partial sums, seeing if it heads to some number, if it just keeps growing. Right now we're at about 3 at S of 10. 999 was too big. Try 99. We get 3. Your calculator actually says 3. It's an approximation. If you think about it, it's never actually getting there because you're always adding a fraction a little bit closer to that number 3, but it approaches. A convergence, to say it converges to 3, means it's headed there and it's not going to go past it. It's just going to keep getting closer to it. So this one does converge to 3. Now that's numerically testing it, but there's ways, of course, we're going to do it more precisely. So we're not really getting to 3, just approaching. What's weird, again, is the idea that the limits, we know that as n goes to infinity of 3 over 2 to the n equals 0, we're adding pieces that eventually get infinitely small and eventually added on to the 3 halves and all those, it accumulates only to something at 3 or below. Very wild ideas. Again, plays with your head. This is the sum of smaller and smaller amounts, and these are all the kind of the notations that go with it. So hopefully this gets you just started. This is called a geometric series, by the way. Remember, geometric is a repeated multiplication of some number, something to the nth. And you may not see it in here, but this is 3. If I rewrite this a little bit, it's 3 times 1 over 2 to the n, which is the same as 3 times a half to the n. So it's geometric because we're repeatedly multiplying by half, half and half and half and half. The next one is also a geometric series, but it's a little different look. This one is like an exponential growth where we have a rate, we're adding 1 plus something, we're getting a number, a number larger than 1 is being raised to the nth power. So look at each term in that series, they're getting a little bigger and bigger and bigger, and it just grows and grows and grows. And if you add those together, pretty convincing that it's just going to grow to an infinite amount, and it does. So this one diverges. To do the partial sums on this, you can kind of see how quickly they grow, but ultimately you're seeing a pattern here. So what we want to identify, though, in these two series is their rate of growth. The ratio of growth, this constant ratio of growth, is important. So in the first one it was a half. The ratio is the thing being raised to the power of n. And then the other one was 3 halves being raised to the n, and 3 halves diverged, 1 half converged. And if you're looking for kind of a pattern that goes with it, it must have something to do with being less than 1. If you're raising that to a power of n, it converges. If it's greater than 1, it diverges, and so on. And hey, if you haven't asked Mr. Harder to pause and go back, you should do that, and it's totally your prerogative. I know you guys say I talk really fast in my videos, but I'm trying to, put technology to the test. You can always back up. Or not. And you can just come and tell me later that you couldn't follow my speaking too fast and my writing too fast, and that'd be fine. But try and rewind first. Okay, so converge and diverge because of that ratio being less than 1 or greater than 1, respectively. Shall we continue? Then I get this. This is the generalization. Let's talk about this thing called a geometric series. The geometric series test, we like to call it. So if we do these sums and the sum notation, if you look at the geometric series in the two forms up there, a is some constant, and in fact you can pull the a out front. That's something we should talk about. You can actually ignore, like we did in a lot of like integrals and so on. Integrals are a summation, and like integrals we can pull the a out front and kind of ignore it until we plug it back in the end. You can start at n equals 0, n equals 1, any value you want as long as it's in the domain of the function. We're going to start at n equals 0, n equals 1 for our purposes. We just decided that a geometric series diverges if that rate, that growth rate, or ratio, is greater than or equal to 1, and it converges if it's less than 1. Well, it turns out it converges to not just some random number. It actually is a sub 1 over 1 minus r. a1 is the first term. Now, keep that in mind. That is a common stumbling block. It's just the first term, and that, of course, depends on what you're starting with for your n. So you have to take that into account. You have to plug in that initial n to get your first term. Don't always assume it's like the a by itself or anything like that. You have to do a little work to get your first term, and that is over 1 minus the ratio, and you'll get the first, you'll get the convergence, if it in fact converges. So we're going to go to example 8, and if you look at A and B, they should look familiar, but we're going to apply this test to see how it works. So first thing you want to do is you want to rewrite any of these. If it looks like a geometric series, you got to rewrite it in geometric series form. And I can tell it's a geometric series because something's being raised to an nth power. N is the counter, and if you're raising something to n, it's likely to be a geometric series, but you need to rewrite it so that that rate is isolated, like we have here. So it's something raised to the nth power, so you can see what the ratio is at which it grows. Now we're going to keep rolling. If I look at it, and then you have to confirm that rate, which is 1/2, or ratio, is less than 1, so this converges. And it converges to the first term, and that first term comes from plugging in 1 in for n, and then evaluating, which is 3/2, over 1 minus the rate, or ratio, which is 1/2. So it's 3/2 divided by 1/2. I'm sorry, 3/2, yeah, 3/2 divided by 1/2. And so I'm multiplying by 2, and I cancel the 2's, and I get 3. And that's what we got before numerically. This is just the reaffirmation of that. Now, to the next one, 3/2 is our ratio. It's greater than or equal to 1, so we know this thing diverges. It just keeps getting bigger and bigger, and we're done. So that's easier with that one. The last is a little new. We've got this -1/2, and we're interested in the absolute value of the ratio for our test, our geometric series test. That's definitely less than 1, so it converges. And then we have a way of deciding what it converges to, which is the first term divided by 1 minus r, our ratio. In our first term, you want to be extra careful. It's that, plug that 2 in to the actual ratio to get 3/4. Don't just assume it's 3. Don't assume it's 3. You got to plug that initial value in and to find out what that ratio starts, or what your first term is. So 3/4. And then because our ratio is negative, we have 1 minus a -1/2. You have to account for that negative in the ratio. Put it all together. We're doing 3/4 divided by 3/2, so we multiply by the reciprocal. We've got 1/2. So it converges to 1/2. The sum of all those terms doesn't get any bigger than 1/2. Again, crazy to go to infinity. You're adding number after number after number that's not 0, yet it only gets to a finite amount. Mind-boggling. That's it for kind of getting things done today. You get to spend the rest of your time knocking out review 2 and 3. So make that your goal. Have those finished. And then on Monday, I'll take a look at those. And those are going to kind of be our primary grade element. 17 of these go in the grade book. And I want to see your 1, 2, and 3 so I can account for those. And I should be able to post the 2 key, the review number 2, with probably errors. You guys can point them out and maybe do it on the overhead. but I have it up on the overhead, the projector, and if you guys want to pull that out and find some errors in what I wrote, and there I wrote chicken scratch stuff on there. I was just getting myself familiar with the problems enough so I could help you guys. So you want to double check those, but it's up on my projector. And then review 3, I haven't worked through all of those yet, but when I do, I'll show you guys some of those answers, and we can definitely chat. Again, we'll pull out Post-it notes on Monday, and we'll talk about things I want to remember about each review, because in the end, you're going to want to look at those Post-its and use that as your key of kind of your flashcards, things that I need to remember prior to finishing off the course. Have fun today. Sorry, I just put him down for a nap. I'd had him join us in the video. Hang on just a second. I think he's here. Okay, he's here. Graham, you want to say hi? You want to come and say hi? Do you see those guys? Do you want to write something? I'll add a page. You can write on here? Okay. That's Graham writing. Yep. You can draw you a picture. You draw something? Mm-hmm. Yeah? Yeah, you want to play. You can touch it. It's okay. You want to draw a picture for them? Here, do it. Here you go. Wait, draw that picture. You want to draw? Here he comes. He's going to draw for you. Draw that picture. Good boy. Yeah. That's right. We were working on that last night, weren't we? Do you remember what that was? That's good boy. Yeah. Do you remember what you got? Yeah. Do you remember? Yep. That's his infinity. He has a hard time. His infinities look like 8. So good boy. Yeah. Tomorrow we'll work on some other stuff. Hope you have a good time. You gonna say bye? You say bye? Bye. You say bye? Yeah. Yeah. So fun. That's right. There's the boys and girls. Yeah. Okay. Tap, 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 tap. Yep, he's pounding the screen. Uh-oh. This. Yeah. See you later, alligators.